Okay, for the next and final video of this series, we are going to graph another trig function in polar, but this time we're going to use what we remember from chapter 4, which was how to graph trig equations in a rectangular grid. Okay, so I went ahead and did some work and graphed the curve r equals 2 cosine 3 theta. Now in this case, r is not a distance from the origin like it is on a polar graph. Now r is just the y-axis. Okay, and theta is the x-axis. We're used to that. Okay, now remember cosine always starts at the peak of the wave and proceeds from there. Okay, now how did I know that the peak of the wave would be at positive 2? Well, that's because we have an amplitude of 2 in our equation. Okay, cosine starts at the top, goes down, comes up, and that is 1 period, right? Now the period of a normal parent graph would be 2 pi, right? 1 revolution of the unit circle. However, this value here, we called it a b value, that changes the period. And you might remember that 2 pi over b, that's our period. So 2 pi over b, our b is 3, so 2 pi over 3, that is our period. Okay, so I know that this value is 2 pi over 3. And this is going to be halfway from peak to peak. My trough is halfway between 0 and 2 pi over 3. That's just going to be 1 pi over 3. Halfway between 0 and pi over 3, that's going to be pi over 6. And so looks like my increments here are in pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6, which I know is pi over 2, 4 pi over 6, 5 pi over 6, and so on. Okay, so I'm going to show you how knowing about this wave will help us graph this function as a polar equation. Okay, that's today's goal. Now something we already know about this, and if you watched the last video and remember, because it's a cosine function, just like in the last video, we know that our graph is going to be symmetrical along the x-axis or the polar axis. So really, I only need to graph this on top from 0 to pi. I only need to graph the top half, and then we can just reflect to the bottom half, and we'll have our function graphed. Okay, so let's see here. The nice thing about this function that I have graphed over here is it tells me the high and low and intersection points of this function. Okay, if I pay attention to the peaks and troughs of my wave function, that will show me where my outermost points are of my radius and where my function crosses back through 0, 0. Right, which is, well, not through 0, 0, but where it has a radius of 0, right? Where this has a radius of 0, we're going to go through the origin, and where this function has a radius of 0, we cross the x-axis. Okay. Now we wanted to go from 0 to pi, and I noticed that my function is only graphed from 0 to 2 pi over 3. So let's continue this until we at least get to pi so that we have some values to go off of here. So 1, 2, 3, 4, 5 pi over 6. I know my function hits 0 there, and then 6 pi over 6, that's pi. I know that we go back to the bottom. Okay, so there's my function graphed from theta is 0 all the way to pi. Okay, and what did I say this was? 5 pi over 6. I'll just add that in there. Okay, so these 1, 2, 3, 4, 5, 6, 7 points, I can graph those 7 points on my polar graph. Okay, I have those 7 peaks and intercepts on my rectangular graph, and each of those points is a pair of coordinates, right? So this point right here is the point 0, 2. So it has a theta of 0 and a radius of 2. So let's graph that. Theta is 0 and the radius is 2. Well, theta is 0 means I'm pointing in this direction, right? And I want to go out 2. Now, how do I want to scale this? Do I want 2 to be right there? No, because 2 is actually the highest value that r will take, and negative 2 is the lowest value. So if I make this ring 2, then my whole graph will be inside this tiny circle, and that's a waste of a graph. So I'm going to make 2 at least out to here. Okay, so let's go 1, 2. That's good enough. Okay, so let's graph our first point. 0, theta is 0, radius is 2. Theta is 0, radius is 1, 2. So there's my first point. Okay, 2 away from the origin, and then I have pi over 6. My angle is pi over 6, so that's this one right here. I can just label that. Pi over 6 is that one, and I have a radius of 0. So when I'm facing this direction, my radius is 0, which means my point is right there at the origin. Now, how do I connect these dots? That's a good question. These two dots correspond to these two dots, right? And what's connecting these two dots? Positive R values, right? So positive radius values are connecting these two dots, which means that from here to here, I must have a positive radius, not a negative radius, a positive radius connecting these two dots. So I know that they're going to be connected something like that. Okay. Hope that makes sense why we connect them like that, not with a straight line or going down here or going up higher. We know that it's something like that, right? Because we know that pi over 6, that's where this point was. Pi over 6 was the theta value, so I know that my curve isn't going to go beyond that theta value. It's got to kind of sneak in there right at that angle, if that makes sense. Okay, and next we have at pi over 3 a radius of -2. Pi over 3 is facing that direction. Okay, and when I'm facing that direction, I have a radius of -2, -1, 2. So now we're at this point. Okay, and what's happening there? I have negative radius values connecting. My theta is pi over 6 to my theta is pi over 3. So now my radius goes negative, and I connect to that point. Okay. Next point is pi over 2, 0. So pi over 2 is facing straight up here, and my radius is 0. So I know that my graph comes back to 0. Okay. Now, we can actually stop there and reflect, because since we know that it's a function of cosine, it's going to be symmetrical across this x-axis. I can take each of these curves and just flip across that x-axis. If I wanted to, I could keep going and graphing these points. If you do that, you'll see that you'll just have the same points reflected across that x-axis. So that's what I'm going to go ahead and do. Let's see, so right there is going to go to here, and this curve does this and flips back around, and then this part of the curve will be flipped underneath here, so I'm going to have something like that. Okay, and we get a beautiful symmetric rose graph. That is actually the technical term. It's called a rose, and if it has 3 petals, these are actually called petals, or more, then it's a rose graph, and you can have rose graphs with tons of petals. And if you watch that video that I did where I graphed this stuff on Desmos, you saw some roses on there with a lot of petals. Okay, so now just to draw your attention to a couple things. These points here, these outermost points of my rose, those correspond to what points over here? Well, they correspond to the peaks and troughs, right? And this trough down here is actually a repeat of this first point right here. Okay, we ended up back there where we started. So those peaks and troughs correspond to the outermost points of the petals of our rose. Okay, and these x-axis intersection points over here, right? Those are where my r is 0. Well, when we have a radius of 0, we're right there at the origin with a polar graph. So these 3 points represent the 3 times we had to cross 0 to graph this rose. Okay? And of course, if we continued along this this cosine wave, we would just keep repeating and cycling through that rose again and again. Okay? So I hope that helps you see how our knowledge from chapter 4 of sine and cosine waves helps us to graph trig functions on a polar grid. And also we use that idea of a polar symmetry as well. Okay, there's the last video of this series. I hope that it's pretty straightforward and helpful, and I hope you're having fun with this stuff. It's pretty interesting. But yeah, good luck on the homework, good luck on the quiz, and I'll start posting videos soon for the next series. So I will see you guys in the next one. Bye.